Welcome everyone to week 3 of the decision support modeling using Python, GMDSI self-guided notebooks. So this week, the theme is that we are finally going to solve Bayes and get at that posterior. So we're going to talk about GLM and the Jacobian and talk about how we use ensembles to sort of approximate the Jacobian. But before we dive into it, I think I'm going to go first, open up the floor if anybody had any questions about the homeworks from last week. So we went over the obs and weights notebook, which went into how to, set up observations, whether they're secondary or primary, how to group them, how to add observation values, add weights, and then looking kind of at that interplay between weights and noise that Mike went over, but I think the notebook dove into as well. And then we also had a notebook that covered prior Monte Carlo, which was what I went over last week, and which is, again, a super powerful tool. And we're going to kind of follow up a little bit on that today. But before I move into that, I wanted to make space if anybody had any questions or any comments on those homeworks that they worked through. You're muted, Mike.
Yeah, I know. Sorry. Maybe use the hand raise feature or drop your questions into the chat if you had any feedback or questions about the homework.
Did anybody try any of those challenges of trying to break the prior Monte Carlo or do some sophisticated weighting? No, okay. I guess it's Monday. Okay, cool. Well, then I'll just dive right into it. The one thing we didn't cover last week, which I think is still kind of an important aspect of this prior Monte Carlo loop, which is kind of what we were talking about, a loop that you can go through before you even get to any kind of history matching. And it's a really, really powerful and informative process. But sort of an intermediate step between your prior Monte Carlo and going into your history matching is rejection sampling. So I will go ahead and share my screen and talk through what I mean by that. So just to kind of catch everybody up on the prior Monte Carlo and give some examples of rejection sampling. This is that same notebook from Mike's fake repository that we've been working in. And basically, say you're going through your prior Monte Carlo and you feel pretty good about, you don't have too much prior data conflict. You feel pretty good about your uncertainty bounds being, conservative and defensible. And now you're wanting to move forward into the next step and actually do some parameter upgrades, parameter estimation. But you know that, in your prior, you still are kind of exploring some potentially extreme spaces of your parameter distributions. And so you can have things like model fails and non-convergences and mass balance error. And so we use rejection sampling basically to cull that initial prior ensemble before you move into that history matching. In that way, you're not trying to history match what you already know is not stable. You're just going to be carrying that forward and sort of wasting computational resources and time basically on those members of the ensemble. So in order to show this, I had to modify that pest from that we had worked on a couple weeks ago, basically to add a couple new sets of observations, and I also added some more parameters for this demo. So recall we started off by specifying the path for our model files. And then I actually added a little function here that goes ahead and gets whatever executables we need and throws it in there so we don't have to manually copy and paste while live coding, which is pretty embarrassing. And then we do that little test run and make sure everything's working okay. And then we start that pest from, which you guys are all probably very familiar with now at this point, that instantiate that pest from container. And then this is where we added previously just the grid-based hydraulic conductivity for layer 1. And you'll notice I added some bounds here and I actually expanded them a little bit because I want to kind of stress this prior ensemble a little bit just to kind of show you guys the power of rejection sampling. So I've added those with some wider bounds than we had before. And then I've also now added well pumping, so well Q as an adjustable parameter, and gave it some pretty wide bounds here. And I did that because this could potentially stress it to be a little bit more unstable when you start really messing with pumping. So added those to the pest from container. And then you'll see here now, I have this new function, and this is just like you went through in previous notebooks where I built a function called, convergence fails or converge fails, and I built sort of a wrapper function to that to test it. And that basically goes into after you've run your model and grabs your list file and counts the number of times that you had a fail, the word fail appearing in the list file. It's a pretty simple function. So we want to add that to the forward run now, so that every time we run this model in the prior Monte Carlo, if there are fails, then we're going to count them, and we're going to basically track that as an observation, a zero-weighted observation. So we add those now as a read in that CSV, add those observations now. And then we can do the same thing by building that auxiliary function and collecting the information that we need from the list file for something like percent discrepancy for the mass balance error. So that's what I'm doing right here. I have a function that says process that list file, and what we want to grab is the percent discrepancy column from that list file quantity. So now we're tracking that in all of our models. And then we're back to the heads that we had assimilated or added to the pest from workflow previously. So this shouldn't be anything new, adding these heads to the container. We need to add that forward run command, which we always do for our pest from and our forward run process. But then you'll see here, I'm adding those extra pi functions now for convergence fails and processing the list file. So we're adding that, and we're specifying that it's not going to happen before the run call. It's going to happen after it. So that's what we need now to be able to do this prior Monte Carlo with the added step of rejection sampling. So now we can reject members of the ensemble based on something like a phi cutoff, a number of convergence fails tolerance that we're going to set, or a mass balance error tolerance that we can set. So we build that, and we are going to run, just do a control file run, just to make sure everything looks good, nothing failed, and we don't expect there to be any phi because, again, we haven't set any weights yet. And that was what Mike went through last week with his obs weights and then prior Monte Carlo. So we're adding in our true observations. And then this is that loop where we're going to locate where we have true observations in the pest control file, set that observation value, set a weight, and we're also going to give it a standard deviation for the noise. So then this is our initial phi. But then Mike went and added that fancy little phi balancing step here by observation group, basically, so that now we're balancing by each of those heads. And recall, actually, that before that, I've set all of the obs weight to 0. So now everything is 0 except for what we say is not 0, which is just going to be those true values that we have for heads. So all of those auxiliary values that we've added, like the convergence fails and the mass balance error, those I've already made sure are 0 weighted and not going to factor into our phi. So we set n-opt max to -1 for that prior Monte Carlo. I'm just going to do 75 reals here, realizations for that ensemble, write that out, and now we can start the workers. And so while that's running, I'm going to bring over some code to start to, so this is just Panther, and then we get this nice tracking thing here for, we've got 10 members running, and then they'll start to complete and a few will start to fail. So the first thing that we can do for our rejection sampling is we want to take a look at those phis that we get from each of those members of the ensemble right here. So what I have is I'm just reading in that directory where we have that Monte Carlo running. Our Freiberg prior is just our name, the phi actual. And actual here is without the noise. Phi measured is with the realizations of measurement noise here. So we read that in and we can print it out, and right off the bat, because we are having ones fail here, and a few will get timed out as well, we're going to first want to drop any of the ones that are not a number, so nans, because those are not going to get a phi because they are failing. So that can be, sort of your first pass at rejection sampling here. And so while that's still running, I will pull up the next first one that we can look at. So this is just a drop those NAs and then see what we're working with in terms of the length of that. And since we had 75, we know that 75 is the maximum we can have, but it's going to be something less than that because we are having some things fail. And while that is running, we can then also load in that prior ensemble observation file, which right now we're still saving as CSV. With larger models, you would save that as a compressed binary format. But we can load it in and basically find all of the observation column for those convergence failures. And then we can basically set that tolerance. And so we're going to set a pretty strict tolerance for that convergence failure observation type, which is we don't want any non-convergences in this prior ensemble. And so we can just do some pandas subsetting based on that threshold, and we can look at what number of realizations we have from that resulting from. And so I think we should be hopefully finishing up that ensemble pretty quickly. But while that's going, I can add the second one. You can do the same exact thing with mass balance error. So here we're doing the same thing where we've loaded in that that CSV of our observations from that prior Monte Carlo. And now we're just going to set a mass balance tolerance of 5%. So basically any of those runs that had for any single stress period a mass balance error greater than 5%, we're going to want to not include that one in our rejection sampling. So that guy finished. So now we can actually take a look at our phi here. Oh, it's not marked down. This is code. There we go. So yeah, you can see we got, a lot of numbers, a couple of nans. You'll see that there's some, we expect something around the hundreds, but there's some thousands and tens of thousands. So there's pretty wide range in phis, which is what we were expecting because we were kind of setting some wide bounds on that pumping in that K. And so after we drop, those nans, we've already gone from 75 to 55 in our ensemble. Now, if we want to reject by those convergence fails, we lose 3 more. So 3 of those members that, still solved because we're setting in the, I forget which modflow 6 file it is, but you can specify continue so that the model continues to run even if you have a convergence failure. So only happened 3 times. If you reject by mass balance error, and we only drop 1, so only one of those, after you drop those nans, only one of them had a mass balance error that was above 5%. And lastly, we can just reject by phi. And I'm only saying lastly in terms of the order of which I'm just copying and pasting here, not necessarily a priority for how you should go about this. So let's say we recorded that initial phi from that first run with the base, observation values and control file parameter values. And then we just said arbitrarily, let's say we don't want anything above twice that original phi that we got. And so that's our tolerance for that one. And that actually reduces it down quite a lot. Now we're down to 27. And then these are the indexes basically of the ones that are still good or good enough. And so then this doesn't have to happen independent of each other. Mike and I were chatting earlier, and he goes basically first by phi, and then once you've culled the ensemble down to the ones that have an acceptable phi here, which we're not in any way recommending that this is the cutoff. It's obviously a subjective thing. It's again up to the modeler to make that decision of what is acceptable. But once you've culled it down, then you can also reject anything that still has convergence failures in that or still has mass balance error. But if you start with this, you'll often find that there won't be many that you drop once you drop the ones that have poor phi. So let's just say we're going to go with that phi, and then you can take that, and the value of this now is that you've dropped out all of those unstable runs, and you've also been doing this larger prior Monte Carlo loop, right, of revisiting your assumptions and your model structure and conceptualization, and maybe you've gotten to a good point with that, and now you've culled that ensemble, and so you have this, super stable and fits whatever criteria you have ensemble to then move into history matching, and you're just going to really set yourself up for a much better outcome, I would say, both in terms of computational resources and in terms of what pests can actually do in terms of the parameter upgrades and minimizing phi. And I'll go after a little bit later and talk about how we then can take this and hot start IES from this place. But for now, I'll just leave it at here. Does anybody have any questions about the rejection sampling? Great. Clear as mud.
100%. Cool. Yeah, so should we move on to the GLM? All right. So basically, we've been talking a lot about the mechanics and about, so I'm just going to share my screen here. We've been talking a lot about the mechanics and the prior is super valuable. But we ultimately want to make some kind of an update, right? And so just thinking back to Bayes again, basically, all of this information, when we start and sample our parameters from the prior, we get some distribution that we're defining, and it's based on this is again our sort of our best estimate of how we think the system works, what we think are reasonable values, and as Katie showed, we don't necessarily those bounds aren't necessarily exactly right. We're going to have some extreme values or extreme combinations of parameter values that give us these unrealistic objective functions or objective function values. So that's why we did all this rejection. But we can cascade this out. We also get a similar distribution of model outputs for each of these parameter sets. And that's still just the prior. We don't fully execute Bayes' equation until we take the prior, mix it with the misfit that we're seeing in the model outputs, and then find this compromise between the two that we call the posterior. And it's been updated, right? And in the past, when we weren't running prior Monte Carlo as often, this kind of loop was where we spent most of our energy. We would be trying to get to new parameter sets all the time. But the prior Monte Carlo is giving us this great opportunity to reevaluate our subjective information first as many times as we can, learn a ton about the model, and then only then do we actually solve Bayes' equation. Do we actually get to the posterior? But then how do we do that? How do we actually mechanically get to the point where we're making a new set of parameters using the information both from the prior and from the posterior? So we'll skip the prior for the moment and just go from, if we have this information about the misfit, about the discrepancy between modeled outputs and observations in the world, how can we use that to update the parameters in a meaningful way? And there's a variety of ways to kind of look at this. I'm going to share some notes, and I apparently can't share to the chat. So maybe I will, Katie, I'm going to give this to you in Slack really quick, and maybe you can stick it in the chat in case people want this later. Actually, I did earlier, right? So if you can stick that in the chat, these notes that I'm going to share. So this is very mathy. We're going to, but I don't worry about every single step of the linear algebra here. You can read this at your leisure. But just wanted to introduce generally what's happening here. So basically, if we express the system that we've got in terms of linear algebra, Y is a set of observations that we see, that we've actually observed. Beta are parameter values, and X is representing the model. And so ideally, we should be able to use this relationship to go from, if we know what the model is like, and we know what the observations are, we should be able to run this in reverse and get a new set of parameters, sort of an optimal set of parameters. And we'll explain in a minute what's optimal about that. But key to all of this is we need some kind of information that is sort of relating the observation space to parameter space. We need some kind of relationship there, and that is called the Jacobian matrix, which sometimes is expressed as an X, sometimes is expressed as a J for Jacobian. But this is really basically a gradient from observations to parameters. But this, if we were looking at it this way, this doesn't include any kind of error. So if we thought that we knew we had a perfect model and we had error-free observations, then this relationship and everything was linear, we should be able to do this all in one easy step. But right away, we have things complicated by knowing that we have some errors. And we're going to add that to this relationship, and it's just called epsilon. So however those are structured, we know that basically the information contained, this kind of goes back to the observation weights and noise that we talked about last week. These errors are various things. They have to do with errors in the measurement of Y, of the observations. They have to do with the imperfections in the model. So we don't expect, if we run the model with a parameter set, we never expect to perfectly represent these observations. And so, and we talked a little bit about the objective function being the sum of squared errors. So if we square these things and we want to minimize the sum of squared errors, we do that like you do it with many different other functions, which is just taking the derivative of that quantity with respect to what we want, which is the parameters, and setting it to 0. So we're just taking some kind of a surface or a curve and finding, the tangent where it's at its minimum point. And so like we would do with lots of other things. A bunch of algebra happens, but then what we end up with, if we do it this way, is this slightly different expression, which has the Jacobian repeated in a couple different ways, and then multiplied against the observations to get us back to parameter space. So if we had no error, we should be able to just take the inverse of this. We should be able to basically, take the inverse of the Jacobian, multiply it by the observations, and get the parameters. But in the presence of error, we get this little bit more complicated equation. This is called the normal equations, but it's also known as the Newton solution. All right, so that was kind of a lot. I'm going to back up a second and introduce this idea called a response surface, which is a way that we can kind of look at this. So I'm just going to, switch notebooks again, or switch screens again really quick. All right, so this notebook is in part 1 of the notebooks that you have, and so there's a bunch of logistics. But now, let's take a look. If we only had 2 parameters, we can kind of visualize the geometry of how this kind of optimization, finding that minimum, would look. And we can just take a grid of, in this case, hydraulic conductivity and recharge, common choices of things that we might want to estimate in a groundwater model. And if we have observations just of heads, and at every point in this grid, we evaluate the misfit. So given a K of 4 and a recharge of 8, the objective function would be somewhere around 100 here, or I guess like 60 or something. And then we can run this in a grid and come up with actually what's called a response surface. The Jacobian is the slope along that response surface, and we're looking for the minimum, right? So at any point, if we start at some combination of parameter values, we should be able to calculate the Jacobian, and hopefully that should point us toward the minimum of the function. And so if we start here, you can see the contours going down toward this area. If we start over here, it's even steeper and it's pointing to this area. But we're always faced with this really challenging problem, which is that the solution, the combination of parameters that give us the same objective function value, can be very non-unique. This is often called like the trough of despair. And the reason is, anywhere along here, we've got like a combination of conductivity, hydraulic conductivity and recharge values that give us the same low value. And it's really non-unique. And this is pretty well known if you actually look back at the groundwater equations. The hydraulic conductivity and recharge are very well correlated. If you increase hydraulic conductivity, that's going to tend to lower heads. And if you increase the recharge, that will bring the heads back up. So there's kind of an equilibrium. If you increase both, the heads will stay pretty much the same. And if you decrease both, the heads will stay pretty much the same. And that means the misfit will be pretty much the same, and you're in this trough. So one important thing in constructing an objective function is trying to break that correlation. So if we add a flux observation, in this case, if we think back to this Freiberg model that we've been working with, the heads are scattered around here at the X locations, but we've got this river and we have a couple measurements of flux, right? So that gives us a sense of the water balance, which will also give us a sense of the recharge independent of the heads. And that can break this correlation. So now if we just add a flux observation and give it a meaningful weight, we start to get like a more defined minimum of this function. And this is exactly what we want. It's not this correlated trough. There's kind of an area that is more unique, and that's super helpful to look at. So if we construct things in this way, you would think then that we could just start with some combination of parameters, calculate the Jacobian matrix, and start going to town and finding the slope along this surface. And we can certainly do that. The Newton step, which is the one that I showed in the equations with the transpose of x transposed with x, it's kind of like squaring x, which is an approximation of the second derivative. And I'll just say the first derivative is the slope of the surface. The second derivative is kind of the curvature of the surface. So the second derivative gives us information about like ridges in the surface beyond just the slope. And that can really lead nicely to actually kind of a good location more directly than just taking the steepest descent or going with just the Jacobian. So if we started with just the Jacobian, we calculated a step, and from this point as a starting point, it would point directly downhill, so to speak, which is great. If we got right here and then we recalculated the Jacobian again, it would point this way. Those are pretty good directions, but a lot can go wrong. One of the things that can go wrong is the step can be actually too far and you can go up the other side. And people call this hem stitching because you might just start going back and forth, kind of like a sewing machine, or it's like sloshing. If you're thinking of water like going down a trough, that's not nearly as helpful and doesn't guarantee that it's going to get us here in an efficient way. Using the curvature points in this very different direction, which may be great, but it also it can also kind of go off the rails and start pointing in weird directions. So there's a correction which is in the notes. I'm not going to show the math of that right now, but the point of it is there's a correction to this direction that can trade off between what is the steepest descent and this curvature informed direction, and maybe find a really efficient medium in between. So if we don't use the lambda, in 5 iterations, we might end up getting here to this good place, and this is actually not terribly inefficient. If we use this correction, though, but one thing that we'll see if you look really closely, once we got really close to the minimum, this thing started to jump around a bunch. In this really simple case, that wasn't too big of a deal, but that can be more extreme and can prevent you from really finding the minimum. And so this lambda correction isn't going to the steepest descent, but it's kind of in between and keeps us on a really nice linear path that leads ideally directly to the actual minimum, the actual optimal parameters that minimize the objective function. It takes a few more iterations in this case. And part of the reason for that is that we're adding information in a way that shortens the steps a little bit. So without the lambda correction, the steps can be pretty big. As we start to add lambda, we bring in a little bit more of this gradient information, but we also slow down the progress and make shorter steps. And taken to the extreme, if you use a really high lambda, oops, sorry, this guy. Let's have to, I don't know why it's showing all the output of every model here. That's awesome, eh? Okay. Sorry, I'm going to jump back to the other notes because something got goofed up in my notebook here. Oh, it looks like, yeah, okay. Hold on 1 second, sorry. Right, this is a slightly different surface, but the same principle. So, so if we have lambda engaged, it's kind of in between and takes not a huge number of steps. But if we make lambda really high, we actually end up at the steepest descent. So this ignores the curvature stuff and just follows the steepest descent. But to avoid that kind of sloshing back and forth, it reduces the step size dramatically. So this is actually an awesome trajectory that goes directly to the minimum, but it takes way, way more iterations. And so that's not ideal. So some kind of trade-off among these is really important. And, as a practitioner, you may wonder, well, what should I specify for the lambda value? And the answer is we basically have no idea. It's really difficult, like a priori, to have any good sense of what this value should be. So even in the early days of PEST, before we started using the ensemble approach, we were assigning a lambda value and just using sort of a grid search that evaluates several values of lambda and determines among those values which gives the best reduction in the objective function, and then uses that solution to go into the next iteration. This may seem kind of theoretical for these practical applications, but the reason that we felt like it's useful to kind of go through it is because roughly half of the time of running PEST is waiting for these lambda updates to happen. So we just wanted to kind of give some background as to why that's happening in the first place. And so right, I think that was the main points I wanted to make with that. Except one other thing to go back, this equation I should add to this, but so this Jacobian matrix, as you can see, is really at the center. We need this for all ways that we're going to get to evaluating the posterior, that we're going to actually update parameters. And the most direct way to calculate this is through a finite difference approach, which basically means for every parameter value, we want to increment the parameter. So we get like delta B down here. We'll increment that single parameter and see how much that changed all of the observations and sort of just divide those results. And that fills up a row of this Jacobian matrix. So it's the number of observations by the number of parameters. And for every parameter that you run, you're going to get like the response for every observation. That's cool, but that requires a model run for every single parameter that you have that you're trying to estimate. And in practicality, we have been advocating, and you saw through the PEST setup, we think that there's a lot of parameters that we should be estimating. And part of the reason is if we're trying to characterize the uncertainty if we're trying to calculate or characterize the uncertainty of our results, even just in a prior Monte Carlo way, any parameter that we don't allow to change, we are implying we know perfectly. That's the implication of that. We're saying there's no uncertainty, that thing is perfect. And the grand total of things that I know perfectly about my model, actually there's only one thing, which is that I don't know anything perfectly. Like that's the only thing we know. Everything has some variability. Everything is an approximation, or it's not measured perfectly accurately. And so we we really advocate for bringing a lot of that variability into the problem. Even if we limit the amount of variability, at least some variability is powerful, which means that basically we need to make those into adjustable parameters. That means a model run for every parameter starts to get really cumbersome. If your model even takes 2 minutes to run, but you have 10,000 parameters, even running in parallel, that's going to take a really long time. Before the iterative ensemble smoother approach came along, which Katie's going to introduce in a minute, we had some other ways to cope with this. So people that have been using PEST for a while maybe have heard of SVD, singular value decomposition, or SVD assist. And there were some really innovative, clever, and I think great ways to cope with that dimensionality. And those are still relevant. You can still use those approaches, but in the iterative ensemble smoother approach, we can approximate the Jacobian in a really cool way that allows us to break that bond, like not have to run the model once per parameter. And so I think with that, definitely happy if there are any questions to take a little break and answer a question. Otherwise, we can go to how that approximation happens and how we're going to calculate the posterior here. Katie, we're just so perfectly clear, and concise in our explanations that there's no room for uncertainty or questions. Please jump in if you have any questions, but otherwise we'll keep moving. I'll turn it back to you, Katie.
Great. Yeah. So that was. Oh, look, we got a question. Awesome. You can go ahead and unmute.
I think it's me. I wanted to ask you if you can explain again pretty quickly how the lambda enters into the equations or in the surface that you described, because that part wasn't that clear for me, but I think I get everything from there, but how the lambda appears is not, I didn't get it.
Okay,
entirely.
Yeah, I'll just back up. I'll just show this in an abbreviated way without the maths. So basically, we've got a response surface, and this response surface exists regardless of lambda or anything else. It's just a function of how the observations change with respect to changes in the parameters. And we start in some place on the surface that's probably not the optimum. Our goal is to move to that optimum. And what trajectory we take along the surface can be changed by lambda using nothing else but the information that we get from the Jacobian and our weights and our initial values, like where we're starting on the surface. The lambda can change us from, a trajectory that looks like this and is kind of following some curvature of the surface to the other extreme, which is along the steepest descent of that surface. So the one solution was this way, one solution was this way. Maybe we want some kind of compromise down the middle. And a priori, we don't really know intuitively what is a reasonable value to make that adjustment. And so PEST and PEST++ have to make an approximation. Basically, the algorithm just tries several values for lambda and evaluates how they perform. Whatever parameter update that value of lambda suggests would work, it evaluates several of those and then picks the one that had the biggest reduction in the objective function, which is sort of the most efficient path down this response surface. So that at the end of the day, that's what lambda is doing for us. And it requires a model run for every value of lambda that gets evaluated, because PEST++ solves the update equations and gives a candidate new set of parameters. But the only way that we know how those new set of parameters perform is to run the model using them and look at the misfit. So it just requires a bunch of model runs. So you'll see the calculation of a Jacobian one way or the other, and then calculation of a new upgrade of parameter sets, and then an evaluation of lambda. It flip-flops between those two things. Those two things together constitute an iteration in PEST or PEST++. So calculate the gradients, solve for a bunch of lambdas and evaluate those. And each of those takes a handful of model runs. So that's kind of the summary.
I think you wanted to see, do you have a an equation that shows where that lambda factors in, or?
Definitely do. If you are not interested in the linear algebra aspects of this, you can turn away. But the bottom line is, this is sort of this is the set of equations that we're solving. The Jacobian is in here. Q is a matrix of weights. So the weights play an important role here, as we've talked about a little bit. And what lambda does is, so basically, now just down a little bit of a linear algebra path, in any case that you're trying to invert a matrix or calculate an inversion like this, the more information there is on the diagonal, the more stable that calculation is for the computer. It's just a function of how those calculations are made. And so what can often happen is there's not enough information on the diagonal. So what the lambda does is just puts some value on there. The Levenberg approach that started out at the beginning just put a single scalar value on the diagonal. And then Marquardt came along and brought in a little bit more information from the Jacobian to inform that. But basically, you're just strengthening the diagonal of that matrix. It makes it more invertible, and it also has the effect of changing the trajectory.
And there was one other question. Yeah, about recommendations on lambda scale factor molts in practical use.
Yeah. Oh, sorry. One other thing that we should point out. The scale factor in lambda, I'm just going to grab one of these at random here. Remember, I mentioned this sloshing or hem stitching thing. So if this is the right direction, we don't necessarily know optimally if we should stop here or go a little further. And so in addition to changing the trajectory, PES++ also evaluates just a linear scale factor along those different trajectories. And I would say that's really valuable as well. So to Jack's specific question, I like to evaluate, say, 0.71 and up to like 1.25, 1.3 a lot as the scale factors. And I like to look at a pretty big range of lambda. I think having no lambda, in theory, should be following that information we get from the Newton approximation of the second derivative of the curvature, right? That in theory, that should be more information, and that's a good thing than just the gradient. So I like to have the option for there to be a very low lambda and a pretty high lambda. I would say like maybe 0.1 through like 10,000 is off, or 1,000 or even 10,000. I will say that if you're running PES++, whether you're using GLM or IES, as we're going to talk about, there is kind of an adaptive search that happens based on the first iteration. What range of lambda was the best? The next iteration is going to start kind of focused around that. It's not going to use the whole range again. It's going to start a little bit higher, or if the high one was good, start a little bit higher. If the low one was good, it'll start a little bit lower. So, and I think the defaults are actually pretty reasonable, in my opinion, in PES++. But yeah, I would say a pretty big range of both is I think pretty reasonable.
Yeah, it's sort of like when you're messing with solver settings, right? Like if you're getting to the level of like trying to dial in an IES run by fine tuning the lambdas, it might be more of a question of like needing to go back and revisit the basics of like your prior Monte Carlo. The defaults generally work pretty well. So it's the same if you're starting to kind of fiddle with like solver parameters, like because your model's unstable, it's probably something, calls coming from inside the house kind of thing.
Yeah, actually, sorry, I'll just jump in one more time. Just to summarize, yeah, like you shouldn't really need to touch lambda much at all, but because half of the time of the inversion is running lambdas, we just thought it's useful to kind of take a peek under the hood, but you can just close the hood again and keep going. You'll be fine.
But definitely nice to know how it all happens. Yeah, awesome. Thanks, Mike. And finally, we're like actually on time, which is a miracle. I'll go back
We're learning.
Yeah, we are. Yeah, okay, so the big reveal is that we're not actually solving the Jacobian. We're approximating a Jacobian with ensembles. And, it's a beautiful thing that frees us from those adjustable parameter constraints. But it's not a silver bullet. It's not a panacea. There still are some limitations of approximating that Jacobian. So before we kind of get into that, I was going to show, just kind of picking up where we left off, on how you would then take your prior Monte Carlo and do a hot start for IES. So mainly the thing is that you want to take those outputs that you have from your Monte Carlo. So that would be the parameter ensemble, and then your observation ensemble, and then your observation and noise ensemble. These are the three components you need to be able to hot start an IES run. And again, you don't need to do this, like, if you just want to run it from start, all the way to 2 or 3 iterations, that's totally fine, and probably how most people do it. But this is just a nice thing, so you save yourself that first round of runs, which is great if you don't have infinite computational resources. So all this function is doing is just making a new sort of temporary directory, and then we're going to go through each of these files that we need to restart, which correspond to the various control file arguments. So this would be the IES parameter ensemble, the IES restart observation ensemble, and then IES observation ensemble. Those are the 3 ones that we need to tell PEST in order to have it hot start at the first iteration, rather than rerun a prior, basically reevaluate the prior ensemble. So I'm just reading that in, and then I'm dropping all of those realizations based on the indexes and based on that phi rejection sampling. And I should have said, these are 3 examples. It is infinite what you could decide to do to call your ensemble, and it's obviously problem specific. These are kind of all model mechanics style thresholds. There's also sort of qualitative thresholds, like there's a prediction of interest I have, and if my half of my prior is just like nowhere near anything physically realistic for that prediction, then that's another thing you could do. So basically, yeah, we're dropping the ones that didn't make the cut out, and then we're giving it a new file name with restart, and then we want to rename it because we don't want to overwrite these initial files, because these are, if we're doing a hot start, these are our prior iteration, the 0 iteration. So we don't want PEST to overwrite those. So we give it a new file name, we save that, and then we set that argument here. And so in that template directory, if I go to it now, if I can find it, where's temp? Right here. We can actually go into that PEST file here. So there's those restart files that we just made. And so if I then write that PEST file here. So I'm, for this, just going to run 2 iterations. And while it's running, Mike and I can pause and have a discussion, because the 2 most common questions I feel like we get with PEST is, how many realizations is an appropriate number of realizations for an ensemble? And then how many iterations is a good number of iterations to run? Like, when do you know to stop, basically? And there's some good thoughts on that. But just to pull that up, so now we've just rewritten that PEST, and we have these nice restart arguments and then files associated with it. And now we're going to do 2 iterations without having to reevaluate that prior ensemble. So we're good to go. So I'm just going to run that now. So I give it a master file, or whatever you want to name it. This is going to be the main one that communicates with all those workers. Tell it that template. This is the, we're running IES as opposed to MOU or opt or something like that, and then give it our number of workers and the root directory for the workers. So while that's going, the main thing that I wanted to talk about that is sort of an unfortunate occurrence that happens with any kind of ensemble. So this is not necessarily specific to the approximate Jacobian and iterative ensemble smoother for PES++. This is if you just Google spurious correlation, cross correlation. So much is going to come up in the literature, and it's a lot of ensemble Kalman filtering, and people in the oil industry and in the weather forecasting industry have thought about this much deeper and longer than anybody in the groundwater world has, I think. But basically, and I just lifted this straight from the PEST manual. Basically, when we're calculating an empirical cross covariance, we have lots of parameters and lots of observations, and we have a limited number of realizations. In my case, we're only running 27, which is, suffices to say, generally not going to be enough for any project. You're going to have essentially spurious cross correlations. So basically, just as a function of how we build this approximate Jacobian through ensembles, you're going to have some parameters that are informed when they shouldn't be informed by observations or shouldn't be adjusted, basically. And similarly, if you have large numbers of independent observations, comprising your data set, if you have a small ensemble size, you're pretty much guaranteed to not be exploring, having enough degrees of freedom to reproduce that data. And that's just sort of a fact. It's something that, ensembles are really great, but once again, they're not perfect. They have their limitations, right? So what do you do in this case with the problem of spurious cross correlation? There's a couple solutions, thankfully, that we have. One of which you guys are going to work through in the homeworks coming up for this next week. So you can do what we call localization, where in the PEST world, there's actually a control file argument that's just I forget actually the specific name of it, but it's I think IES localizer or just localizer, like. And it's basically just a CSV, and much like the Jacobian, it's just, you've got rows by columns for observations by parameters, and you basically are telling it which observations can inform which parameters. And so in that way, you can actually go in and try to, a priori prevent that spurious cross correlation. And so some really good kind of simple examples is that we know that heads are not going to inform porosity, for example, and that future recharge won't inform historical heads. So those are kind of the low-hanging fruit that you can do with localization. So there's that temporal thing of any kind of future parameters should not be adjusted based on historical observations. That's probably the simplest one that you can add in. And, the heads and porosity one is also a pretty quick add. It's I think an active debate whether having localization into your workflow or how much localization you do is going to actually kind of slow down the whole process. So there's a trade-off. Potentially, but there's alternatively, you could just run a larger ensemble, and that's this beautiful trick basically of the law of large numbers, where if you just run a larger and larger ensemble, eventually you basically wash out the noise of spurious cross correlations. And so it kind of comes down to, if you have the resources and they can scale, it's probably quicker and just as defensible to just run a larger ensemble. If you're perhaps a little bit more resource limited, and say you have like a fixed number of workers, but you can have them for 24/7 for a really long time, then something like a localization approach might be the way to go for you. I will say the larger ensemble has the effect when it comes to, again, this idea of approximating the Jacobian. The more members you have in your ensemble, the better chance you have that you're going to be more accurately approximating that Jacobian. So that's this sort of trade-off and something to think about. And so what the magic number is for all models, I don't think there really is one, but I know Mike has thrown out the number 300 often. I think he was saying that the oil and gas industry thinks that, something like 500, you don't really see much improvement or gains beyond that. something, I think I usually start with around 400 for your, but it's again something that you can test on your own if you have the ability and the luxury of time to do so. But the larger ensemble also has the effect of being able to explore your uncertainty, because we're always sampling distributions here. So, the more members you have, the more you're able to actually approximate that distribution as well. And so I hope that while I have been yammering on, that completed. And so you can see here, I'll just go all the way up to the top. We started our workers. We had a whopping 27 members of our ensemble to go history matching. And all we had were, again, those heads. And then we were tracking all of those auxiliary variables. And so you can see this is where we get into the lambda calc. So we've solved that approximate Jacobian now. And so now we're going to be testing some lambdas, which these are the default lambdas. And we're looking at, 0.1. And it looks like, yeah, it's basically calculating a couple of different factors here and testing them. And, thankfully it's not too unstable of a model, and we were able to get a pretty good solution pretty quickly. So then we're going through that, take that lambda, take those parameter upgrades, and then we move into our next iteration. And so that's what we're doing right here. So then at the end of it, and this is all in the rec file. The rec file is definitely your friend for anything when you're kind of babysitting a pest++ run, or any kind of pest run, actually. It's got so much information, too much information almost for you. But you can see I had 2 iterations, and so we had that biggest drop from 268 to 108, and then it kind of levels out after that. And so that is where this question of how many iterations is enough iterations, right? I could have followed this out, and I think if you try to give something like 10 iterations, pest++ will like slap your hand and reduce the number down. I think 4 is maybe like yeah, that's kind of the default like limit. So I guess there is too many. It's 3? Mm-hmm. Oh, I thought it was 4 for some reason. Yeah, anyway, so there is such a thing as too many, and not so much that like the risk of iterating, to get that smaller and smaller fee, and I think the notebooks cover this really nicely, is that you're starting to overfit at that point, because this is when you have probably extracted as much information from the data as you can to inform your parameters, but we know that our data is not perfect, it's not comprehensive, and so if you continue trying to minimize that fee, you're starting to basically have parameter compensation, right? So we're starting to potentially push our parameters to some extremes to be able to match data. And the risk of that overfitting, of course, is we're going to have some terrible predictions from that model. And this goes all the way back to that Freiberg experiment that they went through, where, you want actually to have some sort of balance of maybe not the best fee to have some predictive integrity. And so, everybody has their own personal preference. Some people don't want to actually do any kind of data simulation at all. They go through that prior Monte Carlo loop and get to a point where they feel like they've got a good conservative estimate of uncertainty, and they've gone through that rejection sampling and they're good to go. Let's run that forward and evaluate predictions and optimization and the like. But, something around 1 and 2 is generally a pretty nice balance between actually, assimilating that information from our observational data set without overfitting and without potentially compromising our, predictive integrity. So that is my soapbox, and I will step off of it. And I think that leads us with just talking about the homework for next week, unless if anybody has any questions.
I actually wanted to jump in with one quick thing too. Oh, go ahead. Somebody has a question.
I have a small question about the last thing you mentioned. How do we know we are overfitting?
That's a good question. Well, in our notebook world, where we have these really nice kind of numerical experiments, we can actually say, like, this is what the true observations and this is the true prediction, right? But that's not what we get in the real world. I think it's just a knowing that if you start to do too many iterations, that we are starting to push our parameters into more extreme spaces, and it's more a knowing of the limitations of your data set. I suppose. So rather than being able to confidently say we're over predicting, we can confidently say, this is the amount and quality and, compared to the level of uncertainty we have in our model, from which to, try to perfectly match those measurements. Mike, do you have a follow on to that?
Yeah, I mean, it's inherently subjective. So that's a challenge. One thing that I've seen, at least in, the handful of real world IES models that I've run so far, is that you start to see what we call ensemble collapse pretty quickly. So after, one or two iterations, kind of at the most, you tend to see that there's not much variability in the parameters that are estimated or in the observations from them. And if you go out to actually Jeremy and I were reviewing a paper quite a long time ago that went out to 50 or 60 iterations, and their complaint was that all the parameters in the whole ensemble were basically the same. And that kind of makes sense, right? Because you're using the ensemble to calculate these gradients, and they're all kind of pushing in the same direction. Eventually, things kind of converge. That's a little bit of a squishy answer, but the point is you'll see it if you look at kind of histograms of your objective function through, or look at the spread of model outputs, and there's a decision to make about whether you're overfitting or not. Another thought is when we add noise to the ensemble, in theory, as long as you're using a noise ensemble and you believe that noise is correct, it won't actually collapse. Your ensemble will just will fit to the level of that noise. So that's an important safeguard as well. Then you don't have to be quite as concerned about going too many iterations. Yeah.
Good. Thanks.
Yeah, it's a great question. I think, there's always also the people propose oh, what about model validation? But I think in practice that, it would be really nice if we make our predictions and then we're able to kind of resume in 5 years and see how well we did. I mean, that would be kind of the real world experimental approach to figure out if we were overfitting or not. But yeah, like I said, it's pretty rare.
And techniques that are used in other machine learning and other statistical modeling, like holdouts and validation data sets within our data set. We've experimented with that some, and I think it's a good idea in principle, but we tend to, with earth science, especially in our world where we don't have a lot of control often over where our data are coming from, so we're kind of at the vagaries of whatever projects have existed in the area and collected data, and maybe we add to it. But the point is every data point doesn't really represent the same amount of information. So it's really difficult to say, well, leave this area out and only estimate based on this area. They might not have commensurate information. And so that just is a really big problem. Actually, German, this is exactly a question that I feel like we kind of skipped. So I was going to add a quick explanation of this. I'm glad you asked. So if we go back to, and I'm going to use the equations to explain this, but try to explain it conceptually. So if we look back at this Jacobian that we want to calculate, right? We're really calculating the partial derivative of each observation misfit with the base, with the parameter value. And so the traditional way, as you asked, so the question in the chat is, how is it that PES++ can estimate the Jacobian approximately using the ensembles without running once per parameter? So we'll just back up really quickly and say this is how it's accomplished by running once per parameter. You perturb a parameter, and then you look at the model with the parameter perturbed minus the base run without the perturbation. So that gives you a change in observations, a change in Y over change in parameter, right? That's really a close approximation to this. And the cost of this is having to perturb once per parameter value. This is the traditional way. So, and I will say, when I first got introduced to IES and these ensemble methods, not even then, I'm still kind of amazed that this works. But if you run a whole ensemble, you have a whole vector of, if your ensemble is 300, 500, you have that many different different instances of each parameter value, right? And then you run the model. What you basically get is a pile of changes of Y and a pile of changes of B. So and you could kind of like make tons of differences from those, right? Just subtracting any observation value from another divided by the parameter value versus another. This is great. It is a richness of information, but the problem is this dependence. You don't necessarily, it's difficult to know which changes in Y are due to which changes in B. We're hoping that the correlation between those two is telling us something causal. And this is back to when Katie was explaining the spurious correlations are, we could have changes in the observations due to changes in parameters that were just happenstance. It just happens to be that those parameters changed and really shouldn't be changing a particular observation. And so there's a little bit of math under the hood that's kind of helping guide this. But that's why localization and different ways to sort of guide what we consider to be correlated are really important. But at the heart of it, it's basically what we're after is some metric of change in observation over change in parameter. And by running the ensemble, we have just a whole vector of both, and we're sort of picking that apart. I hope that answers that.
There's another question on overfitting. Does it make sense to see what/how many are at their upper or lower bounds? Example, 500 total parameters at end of iteration 2, 500 are at their bounds at the end of iteration 3, 250. Yeah, I mean, I think that's a great, yeah, if you're slamming up against your bounds, I mean, there's a couple things there. It's a good example of you could pause and revisit your priors. You know, a lot of times we go off of where we have observational data of say like hydraulic connectivity, but you know, that's still kind of a limited sample, and we have no idea if this is actually the true distribution of where we're at. So that's one thing which is kind of like muddies the water a little bit at this, but I do think, yeah, if you have a lot of parameters that are slamming up against their bounds, that's PEST trying to explore those extreme areas to try to, you know, minimize that fee just like, you know, a little bit more. And yeah, I think often what a lot of people will do is run it out because it is costly to run these. So run it out to 3, and then, you know, maybe you still just go with 1 or 2, you know, but you have all of them to kind of like look at and explore, and you don't have to go back and rerun it. Although now that you guys know how to restart IES, it's not that awful.
Right.
But yeah, really good questions.
Yeah. Yeah, that's both excellent questions. And yes, bounds are a good way to evaluate this, exactly as Katie said. I will say that in the ensemble approach, having at least some ensemble members hit their bounds, though, is less of a surprise, I would say, than it used to be in just traditional Gauss-Levenberg-Marquardt. Like when we were running a single instance of the model, if parameters are against their bounds, it really meant that it often made us rethink, wait, are these bounds too tight? This seems like it's unreasonable. It is overfitting because it's extreme values to reduce phi, you know, below what it could do. With the ensembles, you're exploring a much wider space. So a few of the ensemble members hitting their bounds and a little bit more roughness to the solution, meaning a little bit more variability in some of those fields, is something that I think we have to live with in order to make the ensemble methods be applicable. And remember that we're looking at a whole distribution, so probably a lot of those bounds behaviors are at the tails of the distribution, really kind of in the center of mass. So it's a great criterion. I use it in my work, and but you know, there's not like a rule. But definitely, if I see, like in your example, if I went from 50 at one to 250 at the next, I'd really want to look like I'd want to have to justify going to that 250, going to the next iteration. Another thing that I found, I'm going to keep harping on this, but like the value of this outer loop around the prior, every time you refine the prior, every time you change the model in response to that first kind of initial information that you have, you're probably getting closer to a reasonable posterior. in a sense, you're updating just by you're kind of doing these ad hoc updates. You actually are approximating the posterior a little bit more. So by the time you're actually running IES especially in recent projects, I find the first or maybe second iteration is almost always the one that I accept, because it has the most improvement with the least the biggest change in overall change in objective function. You see a pretty big drop, and then it kind of levels off. Plus, the ensemble does collapse quite a bit. The uncertainty is reduced quite a bit, but not too much. And yeah, we're making things a little bit more linear by getting closer to good optimal parameters just through this kind of outer loop of heuristically exploring the prior. So it's a big difference. And people that used PEST with the GLM approach in the past, it was not uncommon for me to see 3 or 4 iterations go by and then a big drop in phi, and then it would level off or start to bounce around. So going to 6 or 8 iterations was really common. It's been a bit of a mind shift using IES to think about accepting fewer, but it tends to be better in my experience. Well, cool. I guess there are 3 IES notebooks for next week. One just kind of going through, just running it, setting it up and running it. And then another talking about localization, and another going into more detail about hot start. And the one last thought that I'd like to say about the hot start or the restart is that if in your prior you have some of these really bad objective function values or really bad mass balance, that's often accompanied, at least with models like ModFlow, with a long runtime. So if you're concerned, if you're paying in the cloud or you're competing for resources with other colleagues, and if I ran a model recently where the prior had an average runtime of 2 hours, but 3 model runs went out to 10 hours. And in my prior, knowing that I can cut those off, hopefully once we start IES, we won't have that big tail. It's a lot more efficient to only run models that are going to be kind of reasonable. So there's a lot of motivation for using that, and a little bit of logistics and bookkeeping. So that's why we have a whole notebook on that topic, and hopefully you'll find it helpful.
Yeah, and I'll push this stuff, and so all of this is on Mike's public reimagined adventure repo. So if anybody wants to pull that and try to follow along, you're welcome to. But yeah, I think the 3 notebooks are just everything IES, and then there's a dedicated notebook for localization, which I think is really, really useful if that's something that you're interested in. It kind of walks through a couple different ways you can do it, and then of course there's a nice little built-in automatic localizer that PEST++ has. And then I think there's a notebook dedicated to restarting. So more on that. Great. All right. Well, I think we can wrap it. Thanks, everyone. I think it was best class.
And thanks for the questions. Makes us know that you're alive out there.
Yeah. All right. Take care, everyone.
Thank you. Bye-bye.
See y'all next week.
Bye.